Okay, so let me recall from the previous lecture. So so algebraic geometry is a study of the geometry of the set of common zeros of a set of polynomials. So what you do is that you take a commutative ring R, and then you take the polynomial ring over that ring in n variables, and you take a subset of polynomials, and then you look at the zero set defined by that subset. It's a subset of the it's a subset of the Cartesian product of R with itself n times, consisting of all those n tuples which are zeros, common zeros of every polynomial in this set S. Okay, and then the problem was that so then you associated to this set S the zero set in this n dimensional space over R, and of course we wanted to ensure that this set is not this set doesn't turn out to be the empty set. So what we do is that we assume that we always work over an algebraically closed field. So we take R to be K, where K is an algebraically closed field, and then our situation is like this. We on the commutative algebraic side we have the polynomial ring in n variables over K, and we take a subset of that ring, which means we take a bunch of polynomials which are the elements of this set capital S, and then you look at the set of common zeros in n dimensional space over K, and of course the important thing is that you should not worry about this as a vector space. You should not think of it as a vector space, you should think of this as an affine space, and which means that you are not worried about the vector properties, the addition properties and so on, but you are worried about other properties, rather topological properties, and these topological properties come from what is called the the Zariski topology. Okay, so I have to tell you what the Zariski topology is. So if you remember, I told you that the Zariski topology is declared by declaring certain subsets as closed sets, and these subsets are the loci of zeros of a bunch of polynomials. Okay, so let me elaborate on that. So what I am going to do is I'm going to do the following. The Zariski topology on Kn, of course K algebraically closed field, let me write it here. Okay, so define, so definition, a subset let me say F or let me not even give symbols, a subset of Kn is called an algebraic set okay, if it is of the form Z of S where S is a subset of the polynomial ring in n variables over k. Okay, so look at the definition. What it says is an algebraic subset of Kn, which is k cross Kn times the Cartesian product of k with itself n times, is nothing but the locus of common zeros of a certain collection of polynomials, a subset of polynomials in the polynomial ring with the same number of variables as the number of copies of k you are starting with. Okay, now so immediately you have the following. I'm going to write down some properties, and these properties will tell you that you can always declare, I mean, because of those properties you can declare sets of this form as closed sets, and that will give you the Zariski topology. So here is a lemma. Number one, Z of so the whole space is Z of null set to or rather I should write Z of 0. The null set is Z of well, maybe I can take the whole ring. Third one is Z of S1 union and so on. Z of Sn is Z of S1 dot Sn. Fourth one, intersection for alpha, Z of S alpha is Z of union over alpha S alpha. Okay, so you see this is the these are 4 properties, and let's try to prove them. Yeah, I will explain what this S1 etc. Sn means. It's it's the n-fold products. Okay, so I'll explain these statements one by one. So, well, they're pretty easy to verify. We'll do that. So you see, so the proof, the first one is, well, what is Z of 0? It is all those points in Kn which give 0 when you substitute them in the polynomial 0, but the polynomial 0 is a constant polynomial 0, it always has the value 0 no matter what you substitute in the polynomial. Therefore every point in Kn satisfies this. Okay, so one is obvious. Okay, and what you must understand here is that we are thinking of 0 as the 0 polynomial. Okay, you are thinking of 0 as a 0 polynomial, and the 0 polynomial is also when you substitute the variables in the polynomial, the value of that polynomial is the value that you get is also 0. Okay, so you must distinguish between 0 as a polynomial and 0 as a value of the polynomial. Okay, so the 0 polynomial lives here, whereas the value 0 lives on K, and your so you must understand these two things distinct from each other. Okay, so but in any case this is very obvious, and look at the second question, look at the second statement. If you take the subset S to be well, you know, if you want to be very particular, maybe I can even put I can put this, because I write 0 of a subset, so I should actually give you a set, and if I just write 0 it's just a single element. But normally we have this abuse of notation that if you have a single element you just write for a single polynomial f here, you don't write Z of f within braces, but you simply write Z of f. okay, you avoid the braces. So if you avoid the braces, this becomes z of 0, that is what I wrote first, but to be very strict to begin with, let me write it properly like this. Okay, now look at the second statement. Second statement says that the 0 set of the whole ring is the empty set. That is obvious because in fact any subset of the ring which contains 1, or for that matter any constant non-zero polynomial, will never take the value 0 at any point. Okay, for example, you take the polynomial 1, think of 1 as a constant polynomial, it always has the constant value 1, so it is never going to take the value 0. So there is not going to be a single point in this Cartesian product which if you substitute it is going to give you the value 0, because the value is always non-zero and it is a constant. Therefore this set turns out to be empty. Okay, and look at the third one. So for the 2 is also obvious. As for the third one, I should explain what this S1 through Sn means. So this S1 through Sn means, mind you, all these SI's are subsets of the polynomial ring, and in the polynomial ring you have a multiplication. Okay, so S1 through Sn actually means products. One, you take products consisting of n factors where the ith factor comes from Si. So let me write that S1 Sn is actually the set of all F1 Fn such that Fi is in Si. This is what it means. Okay, you take one member from each Si and then multiply them out. Okay, and then you take the 0 set of that, and my claim is that this and this are the same. So as usual, how do you check two sets are the same? You take something here, show it's there, you take something there, show it's here. So let's try to do this. If you have a point lambda 1 etc lambda n, oops, I think I don't want this n to be the same as that n, so let me change this to m, because this could be any number of subsets, but it has to be a finite number. Okay, so let me change it here as well. If you take an n tuple which is in Z of Si, okay, that what it means is that you take any polynomial in Si and you plug in for the variables this n tuple, then you get 0, and therefore any such product will also vanish. So it's clear, then clearly this point is in Z of S1 etc up to Sm. Okay, that's obvious, because you know, to get a 0 of an element of this means you have to get a 0 of an element which is a product like this, product of polynomials, and for that it's enough just one, or it's a 0 of just one of them, so that when I plug in this n tuple into each of these, even if one of them vanishes, then the product vanishes. Okay, therefore what it tells you is that Z of Si is always in Z of S1 Sm. So this tells me that Z of S1, the union, is in the 0 set of the product. Okay, this is obvious. What is a little not so obvious is the other way around, but which is also very easy to do by, you can prove it by contradiction. Conversely, if lambda 1 etc lambda n is in Z of S1 etc Sm, okay, then you have to show that it is in at least one of the Z of Si for some I. Okay, so how do you prove it? You prove it by contradiction. You assume it's not there in any of the Z of Si. If lambda 1 lambda n does not belong to Z of Si for every I, okay, then what does it mean? That it means then for every I there exists a gi in Si such that gi of lambda 1 etc lambda n is not 0. The fact that a point is not in the 0 locus of a set of polynomials means that there is at least one polynomial in that set for which this point is not a 0, that is if you evaluate that polynomial at this point you do not get 0 okay. So for E, and I can do this for every Si, okay, then if you take the product g1 etc up to gm, this belongs to s1 etc up to sm, but you know g1 etc gm of if I evaluate it on lambda 1 etc lambda n is not 0, a contradiction okay. So what this will tell you is that this n tuple has to belong to some z of Si, okay. So that will give you the inclusion of this into this and we are done, okay. Okay, so it is a pretty simple argument, okay, and well then there is only the fourth one left, which is pretty easy to see, and once we do that we have the Zariski topology on affine in space. So for the fourth one you take a point lambda 1 etc lambda n is in the intersection of over alpha z of S alpha. So here of course you are assuming that S sub alpha is a collection of subsets of the polynomial ring, alpha is the index, and of course alpha varies over some indexing set which I do not want to be very explicit about, that is not what we are not so worried about that indexing set, because we don't there is no restriction on the indexing set, it need not be finite, it could be infinite, okay. So if there is a point in this, that means you are saying that this point vanishes in every polynomial in each of the S alphas. So it means that this polynomial will also vanish, I mean this point will also be a 0 for for the set of polynomials gotten by simply taking the union of all the S alphas, right. This is obvious. What does the top line mean? It means that you take any polynomial in any S alpha for any alpha and you plug in this, evaluate it at this point, that is plug in this for the variables, then you get 0. But that is exactly what this means. If you take all the polynomials in all the S alphas, then they all vanish at this point, okay. So this implies this, and the other way is also obvious. If you have a point here, then certainly that point is going to be a 0 of every polynomial in S alpha for every alpha. So it is going to belong to each z S alpha, and therefore it is going to belong to the intersection. Therefore this is just obvious, I mean, provided you think about it for some time. It is just basic, it is very simple logic, okay. So this is quite clear, okay, it is just set theory. So so that is the well, that is the end of the proof. It's a pretty simple exercise, but what is the import of this lemma? The import of this lemma is that you can declare subsets of Kn of this form, namely the algebraic subsets, you can declare them to be closed sets. if you declare them to be closed sets, the lemma says that the whole space is a closed set, the empty set is a closed set, the union of finitely many closed sets is again a closed set, the intersection of an arbitrary collection of closed sets is again a closed set. And these are exactly the axioms for the closed sets in a topology. So the lemma tells you, lemma above implies that Kn becomes a topological space if we declare algebraic sets to be closed. Okay, and so this means that therefore the Zariski topology as it is defined here is defined via closed sets, and of course the open sets are the complements of closed sets always. So let me mention that this is a Zariski topology. This topology, this topology is called the Zariski topology. And Kn along with this topology is denoted A n k and called affine n space over K. Okay, so you see we stripped off we stripped off the vector space structure, but then to make it into a different thing we called the affine space, we added the Zariski topology. Okay, and this is the affine n space over K, right. So things are quite good. If you look at this picture, there is the so the space on this side has at least become a topological space. So the moment it becomes a topological space, you can at least start thinking of continuous functions. Okay, once you have a topological space, you can at least think of continuous functions. And of course the first question that one would ask is, these are of course the polynomials are of course functions on this space, and then you would ask, are they continuous? And the answer is yes. Okay, it's an exercise, but we will also see it in some other way later. So it will happen, maybe if you want you can try it out as an exercise, that you take any polynomial here and think of it as a map from Kn to K, evaluating every point on that polynomial will produce a element of K. So every polynomial becomes a function on this affine space, and then check that that function is actually continuous for the Zariski topology, because the source space is Kn with the Zariski topology, which is an K, and the target space is K, which is a1 K. Okay, so fact, or I'll put it as exercise, but we will see this later in detail. Any f in k x1 etc. xn gives a continuous map from an k to a1 k. That's essentially enough. It's essentially enough to check that the it is essentially enough to check that the inverse image of any point is a closed subset. Okay, but but it is an exercise, you will have to do some work, okay. So so you see there is some there's some cyclicity going on here okay. See, in the usual topology, when we study, suppose you study real valued functions or complex valued functions, then the set of points where the function vanishes is a closed set. Of course I am only worried about continuous functions. The set of points where a continuous function vanishes is a closed set, right, and the reason for that is topological, because a single point is closed as a subset, is a closed set, and the set of points where the function is takes the value 0 is the inverse image of the singleton consisting of the point 0, and that is the inverse image of a continuous function under a continuous function of a closed set, so it has to be closed, okay. So the set of points where a continuous function takes a fixed value is always a closed set. I mean 0 is a special value, but it could be any other value, and we use that kind of intuition to define the closed sets here to be given by the loci, the common loci of where a bunch of functions vanish, okay. But then what this exercise tells us that it vindicates our stand. I mean it tells you that our original intuition is correct, okay. If our original intuition to declare 0 sets, 0 loci as closed sets is correct, then our functions using which we declared these 0 sets as closed sets, they should of course be continuous, and the fact is yes, okay. So this is an exercise, it's pretty easy to check, but I will come back to it later in a more general form, okay. So so the point I wanted to make is the next point I want to make is again I think I will need this diagram again, so I'll okay, so let me again draw the diagram. I will keep needing the diagram again and again. So here is the so let me do that. This is geometric side, and this is the commutative algebraic side. So on the geometric side you have an k, which is actually kn plus Zariski topology, alright, and on the commutative algebraic side you have the polynomial ring in n variables, the same n as this affine space, okay. And what we did is, well, we started with the subset here and then we associated to this an algebraic set which is a set of zeros, and this is actually closed. By definition our algebraic sets are the closed sets, okay. And how do you get more general closed sets? You get more general closed sets by either taking arbitrary intersections of such closed sets or by taking finite unions of such closed sets. That gives you all the closed sets. Now, well, what I am now next going to worry about is this side of the picture. See, on this side of the picture what we have is just a subset, okay, and a subset of a ring is not a very interesting object by itself, okay. Usually, so the way I am asking you to think is, whenever you look at an object you try to think of sub objects in the suitable sense. So for example, if you are thinking of groups, then you should think of subgroups, okay. If you are thinking of for example, if you are thinking of vector spaces, the interesting subsets are subspaces, okay. So the same way, if you are thinking of subsets of a ring, what are the interesting subsets? The interesting subsets are, well, one could be ideals, the other could be subrings, okay. But there's no point in taking a subring here. The problem is, if you take a subring, then it contains 1, and the moment it contains 1, z of 1 will become empty, because you know z of s will always become empty the moment s contains a unit, because a unit is a constant polynomial, it's a non-zero constant polynomial which never vanishes. So if your subset S contains a unit, which in this case is a non-zero constant, then the 0 set is going to be empty. So there is no point in taking a subring here. So the fact is you don't want any units to begin with, because if you take units here, this set is empty, there is nothing to study. So what are the other subobjects you can think of? They are ideals, and you know an ideal is non-trivial if and only if it doesn't contain a unit. The moment the ideal contains a unit, which is an invertible element in the ring, then the ideal has to be the whole ring. Okay, so what this tells you is that it's the interesting things here to look at from the commutative algebra point of view are the ideals. Okay, but what we started out is just a subset. Now how do you go from the subset to the ideal? There is always a philosophy for this. Whenever you have an object of a certain type and you have a subset and you want a subobject, what you do is you take the so called subobject generated by the subset. Okay, so if you have a group and you have a subset of a group is not so interesting, but you can always take the subgroup generated by the subset, which is the smallest subgroup which contains that subset. Similarly, if you have a ring and you have a subset, if ideals are what you are interested in as subobjects and not subrings, then you can look at the ideal generated by the subset. Okay, so what you can do is you can think of replacing this set S by the ideal that is generated by S. So what we will do is, let us do the following thing. Let us write S, let me use the following notation. I will put S with a round bracket, and S with a round bracket means the ideal generated by S. Okay, so this is the ideal generated by S in this polynomial ring. Okay, now what is this ideal generated by a subset in the polynomial ring? Of course there are two ways of describing it. One is this is equal to the smallest ideal of ideal containing S. This is one definition. Okay, and what is the smallest ideal containing S? How will you define the smallest ideal containing S? It should, well, it is first of all it has to be an ideal which contains S, and it should be smallest among these, which means that if there is any other ideal which contains S, that should contain this as well, which tells you that this is the intersection of all the ideals which contain S. So there is another way of stating this said theoretically, this is the intersection of all ideals J over J where J contains S. Okay, and of course you know when you want a smallest subobject containing a subset, this is what you always do. You take the intersection of all the subobjects which contain that subset, and usually in good situation the intersection of all these subobjects will again give a subobject. Okay, so if you take the intersection of a family of ideals, that is again an ideal. The intersection of a family of subgroups is again a subgroup. Okay, so if you want a subset generated by a subgroup generated by a subset of a group, all you have to do is simply take the intersection of all the subgroups which contain that subset. Similarly, if you want the ideal generated by a subset of a ring, all you have to do is just take the intersection of all the ideals which contain that subset. Okay, so that is the smallest ideal containing S, and there is another way of writing it out. The other way of writing it out is just take S linear, just take the ring linear combinations of finitely many elements of S, just take that. Okay, so let me write that down. This is equal to the set of R, so you know K x1 etc xn linear combinations of finitely many elements of S. That is what it is. That this is the same as this is an exercise. I mean, if it's a simple exercise which you should have come across in a first course in commutative algebra, but if you haven't done it, it wouldn't take you probably more than a couple of minutes to do it. And of course, what does this mean? This means that this is a set of all elements of the form sigma fi gi I equal to 1 to L, where fi are in S and the gi are in the in K x1 etc xn. This is, so you are taking finitely many fi's from the set S and then you are multiplying them with coefficients which come from the ring, and then you are taking a linear combination, okay, and you can check that this is the same as this and that this is the same as this. That's a very simple exercise, okay. So well, the fact is that the picture here becomes better because this is an ideal, and that is a nicer object than just a subset, because on the left side you are looking at a commutative ring, the interesting sub objects are ideals. And then of course the question is, you take Z of this, take because that's, after all, it's an ideal there, but an ideal is also a subset, so you can look at the set of common zeros, and the fact is that you don't get anything new, you get the same thing. That's the beautiful point. The beautiful point is, see, if there is a point here, then it is a common zero of every polynomial in S. Therefore if you take any combination like this, it will also be a zero of that, because every term contains a factor from S and there are only finitely many terms and every term looks like this. So something here is always here, okay, and because this is a subset of that, okay, something here is also here, okay, because when I take ring linear combinations I can set all the gi's to be whatever I want, so I could set all but one gi to be 0 and that one gi I can set it to be 1, okay, then I will get that a point here will be a 0 of each element of S. So this will also be there, I mean that will also be here. So the moral of the story is the same. So what is significance? The significance is that instead of looking at 0 sets of a bunch of polynomials, because a bunch of polynomials, a subset of polynomials is not so very attractive, it's not so interesting from the ring theoretic point of view. If you look at the 0 set of an ideal of polynomials, things look better, because an ideal is something that is a ring theoretic object, and passing from a bunch of polynomials to the ideal doesn't do you any harm, because the 0 set is not affected, okay. So so this tells you that somehow now the story is getting better. On this side we have closed subsets, and on that side you just don't have subsets, you have ideals, okay. So you see slowly you are getting some kind of a correspondence. Here you have closed subsets which are the algebraic sets, and they are supposed to be 0 sets of bunch of polynomials, but you can as well take them to be 0 sets of ideals. So on this side you have ideals, okay. Here you have subsets of, here you have the closed subsets of affine space, and there you have the ideals in the polynomial ring. So you already have the picture on both sides becoming clearer. On one side you are studying ideals of the polynomial ring in n variables, on the other side you are studying the closed subsets of affine space, okay. So this is how ideal theory enters into the picture, okay, but it doesn't enter without its share of apprehensions, and they are as follows. See, the fact is that the worry comes from very simple observation. See, even if my set S was a single element, suppose S was a single element, that means S is only one polynomial, okay, then Z of S is just the 0 locus of that polynomial. This is a set of points in where that polynomial vanishes, okay. But if you take the ideal generated by that polynomial, it's a principal ideal. It consists of all multiples of that polynomial, and that ideal and the number of polynomials in that ideal is huge, okay. You have so many polynomials, okay, and this set is a huge set, okay. If K is infinite, I mean for that matter even if K is finite, but the fact is that since K is assumed to be an algebraically closed field, some field theory will tell you that it has to always be an infinite set, okay. An algebraically closed field cannot be a finite set, okay. So the fact is that this, even if S is a single polynomial, this is an infinite set, so it seems to you as if you are looking at zeros of infinitely many polynomials, okay. Now intuition will tell you that if you put too many equations, if you have too many equations to solve, then you may not get any solutions. I mean for example in linear algebra, if you have an if you are solving n so many equations in say n variables, if there are more equations it is very likely that you do not get any solutions, okay. And so you can imagine that if I change from one polynomial to say infinitely many polynomials, I might not get any solutions, so therefore this set may turn out to be empty, but that is not the case. The case is the fact is because of the Hilbert-Nullstellensatz, you know that because you know these two are the same, and since Nullstellensatz says that the 0 set is of a single non-constant polynomial is non-empty, such a thing is not going to happen, but there is something more that is happening, and that is the following fact. The fact is, for that matter, if you take not just a singleton set, if you take any set and take the ideal generated by that, that ideal will be generated by only finitely many elements. So what it means is that you are actually always looking at the common zeros of only finitely many equations. Even if you start with infinitely many equations, if at all you get a 0, okay, then which you will, okay, so long as the ideal generated by those by that subset is not the whole ring, then you are actually studying only the common zeros of finitely many polynomials. So this is so you know this somehow removes this apprehension that you know even though you may be trying to solve a large set of equations, I mean you are trying to get common zeros of an infinite set of polynomials, actually in principle you are actually solving only finitely many polynomials. I mean you are looking at zeros of only finitely many polynomials, and this fact follows from the so called Hilbert basis theorem or Emmy-Noether's theorem, which is one of the fundamental theorems that you study when you study Noetherian rings in commutative algebra. So let me recall that and write that down. So so recall from commutative algebra, a ring commutative with 1 is called Noetherian if every ideal is finitely generated, okay. A Noetherian ring is a ring in which every ideal is finitely generated. If R is Noetherian, then so is R x1 etc xn. a polynomial ring in finitely many variables over a Noetherian ring is again a Noetherian ring, and this is the so called Hilbert basis theorem. Or it is also called, I mean more generally it is called Emmy-Noether's theorem. Okay. So this is a fact from commutative algebra, right. So what this tells you is that this implies that if Z of S is non-empty, okay, then even if S is an infinite subset, the ideal generated by S is F1 etc. up to Fm for some Fi in K x1 etc. xn. So you know what I must remind you at this point is that if I take R equal to a field K, then a field K is of course Noetherian, because a field has, you know, the only ideals in a field are the 0 ideal and the full ideal, okay, and the 0 ideal is obviously finitely generated by the element 0, and the whole field as an ideal is generated by 1. So both, there are only two ideals, they are finitely generated, therefore a field is always Noetherian, and therefore a polynomial ring over a field is also Noetherian by this fact. Therefore what it means is that this polynomial ring in n variables over a field has every ideal finitely generated. So if I start with a subset S of that, no matter that subset is probably even an infinite subset, if I pass to the ideal generated by that subset, because it is an ideal in this Noetherian ring, it is finitely generated, which means that it is the ideal generated by finitely many polynomials, okay, and so this implies that Z of S, which is Z of, becomes just Z of F1 etc. Fm. So the moral of the story is, you know, when we started defining algebraic sets, we were looking at common zeros of bunch of polynomials which could be even infinite, but in principle finally we are only studying common zeros of finitely many polynomials, and that's very heartening, okay. So why it is heartening is because if there are finitely many polynomials, this is something that you can compute, you can do some computation and you can expect that, you know, this is not going to be a computation that will never end, and this is one of the reasons that a lot of algebraic geometry is nowadays done on the computer, okay. So you have some special software programs like Macaulay and Coco and things like that, which allow you to do ring theoretic computations on the computer, and you can do these computations. So you will be doing computations on the commutative algebra side, and from those computations you can get consequences which means something geometrically. So you can try to prove geometrical statements by doing computations on this side, and the fact that you can do the reason why you can do computations is, one of the reasons is this: you are never dealing with an infinite bunch of equations, you are always dealing with only finitely many equations. And in fact you may ask, when I write here for some Fi, it seems as though that these Fi are very abstract, that you cannot catch them, but that is not true. In fact there is if you look at a proof of the Hilbert basis theorem, then the proof also can be refined to a constructive procedure where you can get all these finitely many polynomials, you can really get them, and so you can do this on a computer, okay. I can really do this on a computer, and that is what helps me to do computations in commutative algebra, which when translated to algebraic geometry give nice results, okay. So the moral of the story is, because of Hilbert's basis theorem, the closed sets you are looking at in affine space in the Zariski topology are just zeros of finitely common zeros of finitely many polynomials. So you are simply studying finitely many polynomials, okay. So the moral of the story is that when you do algebraic geometry you are actually trying to look at the geometry of the set of common zeros of a bunch of polynomials, and usually the bunch of polynomials is having coefficients in a certain commutative ring, okay. Even if you go to a general commutative ring but make sure that the commutative ring is Noetherian, then the Hilbert basis theorem will tell you that even algebraic geometry in that very broad sense you are only looking at finitely many equations. So mind you, Hilbert basis theorem will work if R is any Noetherian ring, okay. So this tells you that you will always be looking at only finitely many equations if you are working with coefficients from a Noetherian ring, okay. That's the importance of this, that is the geometric significance, okay. And the other important thing is, of course, you must not forget that we are looking at the case when the ring is an algebraically closed field because of Hilbert's Nullstellensatz, which assures that you really get zeros. That is, it ensures that the zero set is not the empty set, provided this ideal generated by this collection is not the whole ideal. That means it does not contain a unit, okay. So we will see more about that in the next lecture.